In this video, we are going to be discussing electromagnetic energy. That is the energy that is stored within both electric fields, magnetic fields, and indeed electromagnetic waves. Now, we'll essentially be continuing on from the previous video where we combined Maxwell's equations to show that the electric field and the magnetic field can satisfy a wave equation. And we'll be using that result to derive quantities such as the Poynting vector and energy flux and the momentum which is carried by electromagnetic waves. So let's go ahead and jump right into it. So the first thing I want to talk about is the energy which is contained within anything which is electrically charged or magnetically charged. So what I'm going to start with is I'm going to draw out a bunch of charges in space, something like 6 of them for now. But I'm just going to go ahead and say this could be any number of charges, and I'm going to say this is n charges. And so these are all n charges. It doesn't really matter whether they're positive or negative for now, but essentially they're just n charges in space. And we said that the electric potential V, which is experienced by a point charge at any given point in space, is equal to the value of the point charge divided by 4 pi epsilon 0 r. And what I want to ask is, what is the total amount of potential energy that is contained within this system right here? And that would be the total amount of electrostatic energy that is caused due to all of these charges, which of course experience an electric potential. Well, we know that the potential energy, U, we just get by multiplying the potential V times the charge right here. And so if we have 2 charges, say these 2 right here, then we can essentially say that the potential energy is equal to Q1 times Q2 over 4 pi epsilon naught r, where Q1 and Q2 are the values of each charge respectively. So that's kind of okay for 2 charges, but of course we have many charges in this system. And so what we're essentially going to have to do is we're going to have to add together all of the potential energies of all the charges within an n particle system. So to write this out as a sum, we're going to say that U is equal to the sum going from 1 to n of all of the individual point charges right there. But of course, say we're counting the electrostatic potential energy just originating from this charge. Well, you're going to have one from this charge, you're going to have one from this charge, you're going to have one from this charge, and we're going to have one from this charge, and we're going to have one from this charge. But that's only just from this one right here. So we actually have to do a double summation that is over every single charge being the origin point to each individual charge that isn't that charge. So essentially we have to do some quite complicated summations. But if you kind of just picture it for 3 charges, just to make things a lot easier, then if we're trying to calculate the total amount of potential energy, then of course we do the potential energy due to these 2, then the potential energy due to these 2, and then the potential energy due to these 2. So essentially, we're going to do a double summation. So we're going to bring out this 1 over 4 pi epsilon naught out the front, and we are going to sum over the n charges once, but we're also going to have to do a double sum. So I'm going to choose another dummy index j. But of course, this time we are, instead of going from 1 to n, we actually go to whatever this is right here, minus 1, because of course, for our 3 particle charge, we actually stop when we get to the second charge. So this is going to be equal to Qi Qj over the absolute value of the distance between the 2 charges right here. So I know this is pretty horrible to have to think about, but if you kind of want to just understand what's happening a little bit simpler, then just picture this kind of 3 particle system. But of course, if we do this, then we're essentially counting the particles twice. If we think about it again with our 3 particle system, then if we do this pair right here, and then this pair, so that's this one essentially done, and then move on to this pair, well, you'd think according to this formula right here, then the first thing we do is do the potential energy due to this pair, but we've already done that. And so actually what you're going to end up with is you're going to end up with exactly half of the summations which you would have had before, because you don't want to count twice, essentially. So you'll end up with this right here. So now both summations, instead of this inner summation being dependent on the index for this summation, which is kind of what we had before, both now just sum over n right here. But of course we now have this factor of 1/2, which is actually quite important, as we'll see a little bit later. But what we can actually do is we can in fact factor out this qi and put it in here, because of course this is the only term that is actually not dependent on the j summation right here. And the reason why we can do this is because this term right here is actually just a potential term. This is if you kind of essentially use this formula right here to decompartmentalize the potential, then you actually just get the ith potential right here. And so what we can actually write is we can write the same thing again, but with this second summation written as a compact potential right here of the ith charge in the summation right here. So very fiddly stuff, right, this, but I think if you struggle maybe to understand what I've essentially done here, it's probably helpful to just kind of think about it with a 3-particle system and think about how you would find the total energy if you were just dealing with 3 charges, and think about the way in which we obviously don't want to count duplicates, because of course that would not be the correct amount of energy. So after having done that, we can actually step away from summations, and in fact we can transform this into an integral right here. And the reason we want to do that is because more generally in electromagnetism, rather than dealing with lots of little point charges, we actually instead think of it as a continuous charge distribution, which we often quantify using the charge density rho right here. And so you can essentially think of this as going from the discrete case in this example to the continuous case, which is just a density right here. And so to convert this formula right here into an integral, we simply say that u is equal to the integral of 1/2. And of course, instead of summing over charges, we integrate over the charge density rho right here. And we then, of course, multiply by the potential at each point, V right here. Now, I actually have to change what I'm going to use as my volume variable. And it's actually Griffiths that uses a tau term right here in order to represent, instead of just volume, but just generalized 3-dimensional coordinates right here. So instead of writing dV, because of course that would cause us to get confused with the potential, I'm actually going to write d tau right here. So just as an aside, I will write that d tau, for example, in spherical coordinates would be something like r squared sine theta dr d theta d phi if we're dealing with a 3-dimensional integral. But essentially tau can essentially represent anything, and it can represent any sort of dimensionality. But what did we say rho of r was in terms of the electric field? Well, we know that from Gauss's law that the divergence of the electric field is simply equal to rho divided by epsilon naught. But since this could also apply for a material, then what we're actually going to be using is we're going to be using the similar equation for Gauss's law, that the divergence of D is equal to the free charge right here, because we want to try and keep this as general as possible, and so therefore we're going to use the electric displacement vector. And so what we can do is we can go ahead and substitute this into the energy integral right here. And so we're going to get, now there is a similar identity like we use a lot of the time whenever we're thinking about electrostatics, that is essentially a little bit like the product rule, but it applies for taking the divergence of a product instead of just simply a scalar function of a product. And what this identity is that if you take the divergence of a scalar multiplied by a vector right here, so A is a scalar, B is a vector, you get that the A comes out the front and you then multiply that by the divergence of B, and then you add that to B dot producted by the gradient of A right here. And this is a essentially vector equivalent of the product rule for derivatives. And if we look at what's here, we actually have a divergence of a vector field multiplied by a scalar field. So we actually have this term in the equation right here. So if we rearrange this equation, we get the form that we kind of want it in, which is this right here. So we are going to apply this mathematical vector identity to our integral equation in order to transform it into a two-term integral. And so when we do that, we are going to get this right here, which is essentially going to decouple into two integrals, because of course we have this minus sign right here, and we are going to evaluate each integral separately. So we are going to get this right here. Now we can look at this part of the equation, this first integral right here, using the divergence theorem. So remember, we just simply use tau as a placeholder for volume. So we can essentially identify that we have a divergence of a vector right here integrated over a volume right here. And so when we apply the divergence theorem, we get that this first integral is equal to 1/2. And when we apply the divergence theorem, we just get v d dot ds right here, where s is the surface which is enclosing the volume right here. And for the second integral, we are essentially going to, instead of writing del v, we can just simply write this as E, because of course E is simply equal to minus the gradient of the potential right here. And so when we do that, we get a minus sign, which will change this minus sign into a plus sign. And we're going to get d dot E right here, integrated over the volume. So we have two parts to our integral right here. And let's go ahead and look at this integral in a little bit more depth. Now let's think about what's going on right here. We have a surface which is essentially enclosing a volume, which is kind of what the divergence theorem is saying. Any net flux out of the surface right here must be caused by a change which is going on within the volume right here. But of course, we don't have to specify where this surface is. We could be very cheeky and we could actually take this surface to be at infinity right here. So imagine a sphere that encapsulates the entire universe. There's nothing actually to stop us from doing that. So what's that going to mean if we choose this infinitely big surface for our terms right here? Well, we know that the potential V is proportional to 1 divided by R right here. And we know that the electric displacement field D right here is proportional to 1 over R squared right here. And the surface area element ds right here is, well, for a sphere, this is going to be proportional to r squared right here. And so if we have a look at the first part of our integral, which is of course u is equal to 1/2 times the closed surface integral of the potential times the electric displacement integrated over the surface. Well, let's just go ahead and substitute in how each of these terms relate to r. So we have 1/2, and then in our integral we have a 1 over r term multiplied by a 1 over r squared term multiplied by an r squared right here. But because we're integrating over ds right here, ds doesn't actually have a dr right here, because of course ds for a sphere is equal to r squared sine theta d theta d phi. And so you're going to get a bunch of other constants, but essentially you're going to have a d theta and d phi integral right here. And because we're not integrating over dr, then essentially we can just move all the r terms right here out of the integral, because they're all constants. And so we get 1/2, and what are we going to get? Well, this r squared is going to cancel with this r squared, and so we're just going to get a 1 over r term out of the front of this closed surface integral. So we're going to get a bunch of constants that we don't really care about, integrated with respect to theta and phi right here. But of course, we have taken this sphere to be at r equals infinity, because we could choose for it to be at r equals infinity, because the divergence theorem says that we can essentially have a sphere of any radius as long as it encapsulates all of the charge. And so
when r is really large, so as r tends to infinity, then we can see that this whole term is going to tend to 0 because, of course, we have this 1 over r term out of the front, and the rest of it's all just constants because, of course, this is a constant, the d theta and d phi is a constant as well because that's just going to integrate to give 4 pi probably. And so when r is really, really large, then we're going to find that u, this, or at least the first part of this u term, is going to tend towards 0 right here. And that basically means that we can just ignore this whole term, which is the first term in our equation for u. I should have probably written that this is just the first term. And so we get that u is just equal to the second term, which is 1/2 times the volume integral of the electric displacement field dot producted with the electric field right here. And that is going to be integrated over the volume, d tau. Now what we can define is the energy density, or the energy per unit volume, which we often give the symbol lowercase u. And so we say that's equal to du by dv. So it's the energy per unit volume. And so we can write that the energy density u is just, well, it's going to be all of this, but without the integral. So it's just going to be equal to 1/2 times d dot E right here. So that is the energy per unit volume in an electric field. And using the fact that D is equal to epsilon E, where epsilon is the permittivity anywhere, not necessarily the permittivity of free space, because we could be in a material, but the permittivity anywhere, then we can also write this as being equal to 1/2 epsilon E squared. So just as the magnitude, and this assumes that D and E are parallel to each other. Or equivalently, we could write this in terms of just purely the electric displacement, so that would be equal to D squared divided by 2 epsilon right here. So we have this result for the energy density of an electric field. But what we actually find is that for the magnetic field, we actually get a remarkably similar result to this. So whereas in this case we had the electric displacement and the electric field, we can actually just replace these with the magnetic equivalents. And of course we said that the magnetic equivalent of E was just B, the electric field and the magnetic field in a vacuum, and the material equivalent to the electric displacement D was the magnetic intensity H. And so the magnetic energy density, energy per unit volume, is therefore just simply 1/2 H dot B right here. So it's essentially exactly the same thing. And you can kind of go through and derive it in a similar way, but I'm just going to state this result right here. So this is the magnetic energy density. And likewise, we can write this using the fact that B is equal to H divided by mu, where mu is the permeability anywhere. We can also write this as being equal to 1/2 times mu H squared, or it's the same as B squared divided by 2 mu right here. So there we go, that is the energy densities of the electric and magnetic field respectively.
Now we are going to go back to Maxwell's fourth equation, which is of course the fixed version of Ampere's law. And for that equation we said that the curl of H is equal to J plus dd by dt. And this was the general form for whether we are in a material or whether we are in a vacuum. So this is the most general. And what we're going to do is we are going to take the dot product of both sides of this equation with the electric field E right here. So we're going to do E dot curl H is equal to, well, when we dot product E with both sides, we're going to dot product E with both terms. So we're going to get E dot J right here as our first term, plus E dot dd by dt right here. And for this left-hand side, we can actually reshuffle this equation using a well-known vector identity. So the vector identity I'm using is that A dot B cross C, where these are vectors, is equal to C dot A cross B minus B dot A cross C right here. So this is a reshuffling property you can use for the triple products of vectors. When we apply this to the left-hand side, we get that this is equal to H dot curl E minus the divergence of E cross H right here. And this is all going to be equal to the right-hand side. Well, this curl E right here, we know from Maxwell's third equation that this can be written as minus dB by dt. And so we can go ahead and substitute that in to this equation right here. And we get all of this right here. And so rearranging for this term right here, and you'll see why we're doing this in a moment, we get this result right here. And what I'm going to do is I am going to define this quantity S right here as being equal to the cross product between E and H right here. So all we're going to do is we are going to substitute in S for this right here. And so we get this rather long result, but this is actually quite an interesting finding. And to kind of have a look at why this is an interesting finding, we are just going to go ahead and have a look at every single term in this equation right here. Now, this term on the left right here, we can essentially think of this as the total amount of power that is being supplied to an electric field per unit volume right here. So this is the power per unit volume. Now, this term right here is the electric field dot producted with J. And this you can kind of think of as the portion of this total power right here being supplied to just the charge carriers, because of course we have this J term right here. J symbolizes the current flowing. And so this is the total amount of power being supplied just to the charge carriers. Now, this third term right here, this is E dot dd by dt. And well, we know that E dot d is related to the energy density. So this is a rate of change of the energy density. So again, it's a power per unit volume. But of course, it just concerns the electric fields right here. So the electric field and the electric displacement field right here. So this is just purely an electric term right here. And finally, this last term right here is very similar to the third term, but instead of the electric case, it is just the energy per unit volume, per unit time that is supplied to the magnetic field right here, because of course we have this H and B, and we know that the energy density is H dot B, and we of course have a time derivative right here. And so we have an equation which is essentially telling us where a certain amount of energy is going to, how it's kind of being distributed to the various different fields if we have both an electric field and a magnetic field. And so, like I said, we can use that the electric energy density is equal to 1/2 d dot E right here. And we can use the magnetic energy density as being equal to 1/2 B dot H right here. And so what we can do is we can essentially add these two terms together to get the total energy density as just being equal to 1/2 into D dot E plus B dot H right here. And so what we can do is we can, in fact, substitute these last two terms in this equation for just a simple rate of change of the total amount of electromagnetic energy. And so when we do that, we get this right here. And we can just kind of tidy this up a little bit just to make it look a little bit neater to get this result right here. And this is a slightly more compact way of essentially expressing the same thing. And it's saying that the divergence of this S vector right here plus the rate of change of an energy density is equal to minus the product of J dot E right here. But the more interesting thing happens when we actually set this term equal to 0. And that is going to be the case when there is zero current flowing. And so if we take a case of this, we say the divergence of S is equal to minus du by dt right here. And this should look fairly familiar in that this is actually a continuity equation right here. And we've seen kind of stuff looking a bit like this before. Whenever we have a divergence of a vector being equal to minus the time derivative of another scalar, we actually have a continuity equation. And this s term right here is what kind of made it possible. The fact that we defined s as being equal to E cross H is actually what made this entire thing possible. And so this is why this s is actually given a special name. It's called the Poynting vector. And essentially what this s is measuring is actually a measure of the intensity of the electromagnetic radiation right here. And the way in which you can kind of verify that is that on this hand side of the equation, you have an energy per unit volume per unit time term. But on this side of the equation, you have a spatial derivative. And so working backwards, you find that this S has to have units of energy per unit area per unit time, which is the power per unit area, which is just the same as intensity. So this S right here is the vectorized form of intensity, power per unit area. Now, in the last video, we showed that the electric field right here satisfied this wave equation right here, because of course we derived what the wave equation was, and then we found that from Maxwell's equations, we actually got this wave equation popping out. And now it's time to solve this differential equation. Now, the steps needed to take to solve the differential equation are quite complicated because you need to apply, obviously with any differential equation, boundary conditions. And what you find is you get the form of the electric field right here is proportional to a complex exponential, because we use complex exponentials in order to represent waves, of e to the I kz minus omega t right here. So this is like the most mathematically efficient way to represent a wave traveling through space. Now, obviously in electromagnetism, there is no such thing as an imaginary wave that by definition doesn't exist. And so what you need to bear in mind in electromagnetism is you always want to take the real component whenever you want to try and find what's physically significant. So when it comes to the real component, then you find that it is just cos kz minus omega t, because of the Euler identity that e to the I theta is equal to cos theta plus I sine theta, right there. So this is the solution, and you can get to the solution by using a technique known as separation of variables. It is quite a complicated derivation, but I will put a resource in the description for anyone who wants to see how exactly it is derived. But basically, whenever you see a complex exponential as a function of position and time, then you know you're dealing with a plane wave right here. And because, of course, electric field is a vector, the way to write this as a vector is you say that E is equal to E naught, which is also a vector, it's the amplitude, if you like, times cos kz minus omega t right here. Now, we said that Maxwell's equation is given by the curl of E is equal to the derivative of the magnetic field with respect to time. And so what that essentially does is that relates the electric field in free space to the magnetic field in free space. And so what you can actually do is you can actually solve this. If you know the electric field, you can actually get the magnetic field as well. And so what we're going to do is we're going to take the curl of this electric field right here. Now, because it's easier to work out the derivatives of exponentials, because it just essentially gives you another exponential in return, we're going to use the e to the I equation right here rather than the cosine equation right here. And it turns out when you work out curl, and it's a very, very long and tedious process, so I'm not going to do it right here, you actually find that the curl of E right here is equal to I times k as a vector cross-producted with the electric field right here. And this essentially is because the electric field is an exponential, and so when you differentiate an exponential, you essentially bring down a factor of k right here. And what we can do is we can say that this is equal to minus the derivative of b. But what is b? Well, b also satisfies a wave equation. And so we can say that this is equal to
the derivative of b naught times e to the I kz minus omega t right here. So that's good. And what happens when we differentiate b? Well, when we differentiate b, we're differentiating with respect to time this time. And this is going to bring down a factor of I times omega right here. So we're going to get minus b naught times minus I omega times, well, the original b function right here for the magnetic field. And so these two minus signs are going to cancel out to give a positive sign right here. And so we get ik cross E is equal to I omega B right here. So the two i's are going to cancel. And we get the quite nice result that K cross E is equal to omega times B right here. Now this equation has a couple of implications. And the first one is that it's saying that B right here is actually perpendicular to both K and E right here. So what this is telling us is that the electric field and the magnetic field oscillate at right angles, but they both oscillate perpendicularly to the direction of propagation, which is quantified by this K right here. And so you get the hopefully familiar diagram. If you have a way of traveling in this direction, the electric field oscillates kind of up and down in this plane, but you have the magnetic field oscillating in this plane right here at right angles right there. And they're oscillating in phase with the same frequency omega right here. But the other implication is that if we were to just take the magnitude of this equation, so we're going to turn this into a simple scalar equation. So we have Ke is equal to omega b. Well, let's divide both sides by k. We have E is equal to omega divided by k times b. But what is omega over k? Well, omega is 2 pi f, and k is 2 pi over lambda. So if we put this in terms of f and lambda, this will become a little bit more familiar. So we have 2 pi f divided by 2 pi divided by lambda. Lambda's going to go upstairs, times b. The 2 pi's are going to go, and then we've just got f lambda. And that is, of course, just the wave, the very, very simple wave equation, v equals f lambda. So this is just equal to the velocity right here. And so what we've shown is that the electric field is equal to the velocity times the magnetic field. And in the case of a vacuum, where of course the velocity is completely unimpeded by any sort of dielectric, then the velocity is just going to be the speed of light, c, right here. And so in the vacuum case, we find that E is equal to c times b. And this is a very interesting ramification because it's telling us that the electric field is c times bigger than the magnetic field. And so that essentially says that the magnetic field of an electromagnetic wave propagating through space is really small compared with E right here. So that is a very, very interesting finding. So electromagnetic waves are predominantly dominated by the electric field, and the magnitude of the magnetic field is much, much, much weaker than that of the electric field. Now, from here on, we are going to assume that we are in a material. So rather than using E equals c times b, then we are going to assume that the velocity v right here is going to be less than the speed of light. So we are going to make this as general as possible, and we're going to say that we are in a material. So if we go ahead and take this equation, we're going to get E is equal to v times b. What I'm going to do is I'm going to rearrange this for b. So I'm going to get b is equal to E divided by v right here. And if I simply square this equation, I'm going to get b squared is equal to e squared divided by v squared. Now, this might seem arbitrary, but you'll see what I'm doing in a moment. But what is v right here? What is the velocity? Well, when we solved the wave equation, we had to identify mu naught epsilon naught as being equal to 1 divided by c squared right here. That was the coefficient which characterized the speed. Well, this is the vacuum case because, of course, this is mu naught and epsilon naught, but generally we're going to get mu epsilon is equal to 1 over v squared, where v is the velocity of a wave, which is going to be, in this case, less than the speed of light. So this is the more general case. So we can substitute in this 1 over v squared for mu epsilon right here. So when we do that, we get that b squared is equal to mu epsilon times e squared right here. But what did we say our energy density was? Well, we said that the energy density is equal to 1/2 epsilon e squared, and that was just for the electric field. But if we have a magnetic field as well, then we have to add on the magnetic contribution, which is b squared divided by 2 times mu right here. So that is our total energy density. We can substitute in for b squared this result right here. And so when we do that, we're going to get that the energy density is equal to 1/2 epsilon e squared plus b squared. Well, b squared is just mu epsilon e squared divided by 2 mu. Well, the mu's are going to go, and well, we've just got another factor of 1/2 epsilon e squared. So these two are going to add together to just give epsilon e squared right here. But what is our E term right here for an electromagnetic wave? Well, we said that E, if we just write it as a scalar for now, is equal to E naught times e to the I kz minus omega t right here. That was it in terms of exponentials, but we're actually just going to use the real part right here. We're thinking about what the physics of this system is. We're not doing, I guess, any sort of differential equation solving at this point. So we can say that E is equal to E naught, the real part, times cos kz minus omega t right here. And so if we substitute in that value for E into this equation right here, we are going to get epsilon times E naught squared times cos squared kz minus omega t right here. But what did we say the Poynting vector was? We said that the Poynting vector, S, is equal to E cross H right here. But we can also write this if we substitute in for H in terms of the magnetic field B. We can say that this is equal to 1 divided by mu times E cross B right here. But if we just take the magnitudes, then S is simply equal to 1 over mu times EB right here, if we assume everything's at right angles and everything is at the maximum, which in the case of electromagnetic wave is going to be the case. But we know that the magnitude of the magnetic field is simply the electric field divided by the velocity in which the electromagnetic wave is propagating. And so we can swap this out for 1 divided by mu times E squared divided by V right here. But E squared, we know the magnitude of, is just this cosine function right here. And so we can say that this is equal to 1 over mu V times E naught squared times cos kz minus omega t right here. But in fact, we can juggle this 1 over mu V to write this in terms of epsilon, because of course V is simply equal to 1 over the square root of mu epsilon. And so if we rearrange this to get kind of what we've got at the front of this equation, we're going to get V squared times mu is simply equal to 1 divided by epsilon. And so therefore V mu is equal to 1 over epsilon V, and 1 over V mu is equal to epsilon V right here. So we're just juggling things around a little bit. And so if we use that, then we can just transform this first part of the equation into epsilon V times E naught squared, that should have been a squared, cos squared kz minus omega t right here. But what is U? U is just almost the exact same as this, only without the V right here. That was the exact same equation, just without V. And so all we need to do is we can just say that the Poynting vector, or the magnitude of the Poynting vector, is equal to V times the energy density, U, right here. So we've ended up with this incredibly simple result, that S is simply equal to U times V, right here. And just to write this in vector form, we can say that the Poynting vector is equal to, well, we said it's traveling in the Z direction, so we can say that if it's traveling in the Z direction, we can say put a Z hat on that right there. So that tells us kind of a little bit more explicitly what the Poynting vector actually is. It's just the product of the velocity with the energy density. Now, of course, we're dealing with waves, and obviously waves oscillate in time, which kind of makes it a little bit more difficult in order for us to strictly calculate what the properties are, certain macroscopic properties. But if we have a look at this energy density term right here, so we have that U is simply equal to epsilon E squared, and that is also the same as epsilon E naught squared cos squared kz minus omega t right here. Now, this U oscillates very quickly with time, hence this omega t term right here. But if we just have a look and think about what cos squared looks like on a graph, so we have a time on the x-axis right here, and we have our energy density or electric field, it doesn't really matter in this case, oscillating with a cos squared pattern. Now, cos squared oscillates between 1 and 0, and it oscillates at double the frequency of cosine. So if the energy density oscillates like this, then I want to ask the question, what is the average of this right here? And, well, the average is just going to be right through the middle. So that's going to be what the average energy density is over time. And so instead of writing the energy density as a function of time, we can average over time and just simply write that this cos squared becomes 1/2 over a long period of time. And so what we can write is the average energy density is equal to 1/2 epsilon times E naught squared. And because the energy density oscillates as a function of time, then from this equation, this tells us the Poynting vector also oscillates as a function of time. But we can, again, write the average. So we can write that the average value of the Poynting vector, or the magnitude of the Poynting vector, is going to be 1/2 times epsilon times V times E naught squared, right here. But what is the average value of the Poynting vector? Well, we know that the Poynting vector was actually a measure of the intensity. And so what this equation is giving us is this is giving us the intensity, which is the power per unit area from electromagnetic radiation. So just to kind of draw this out, we say we have like a solar panel or something that's kind of facing a bunch of electromagnetic radiation. Well, all this kind of radiation is going to come in, and this is the intensity of that radiation. This is the power per unit area given by this right here. But what is energy density? Well, energy density U is just the energy per unit volume right here. But what is the energy of a photon? Well, an energy of a photon is simply equal to the momentum of the photon multiplied by its speed, which for generally, if we're going through material, will be the velocity. And that is going to be divided by the volume. And so we can say that the energy density is equal to, well, P divided by capital V is going to be momentum divided by volume. And we're going to call this the momentum density, lowercase p, right here, multiplied by the velocity. And so therefore, the momentum density, P, is going to be equal to U divided by V, right here. And of course, this is going to be the averaged out momentum density over time, because of course we're dealing with the average over all of time. But what is this U term right here? This is going to be 1/2 epsilon E naught squared right here. And so this is going to be all divided by V. But 1/2 epsilon E naught squared from this equation is just the average value of the Poynting vector divided by V. And so we can actually replace this with S divided by v, and that is all going to be divided by v, so this is going to group up to s divided by v squared right here. Or we could write this as the intensity divided by v squared. So we find that this radiation can actually be characterized by a momentum per unit volume right here. And so if you want the total momentum, you therefore integrate it over the volume, but there is a momentum density carried by this radiation that's striking the surface. So if there is a momentum, well, what this in fact leads to is actually there is a pressure on this surface right here, and that's simply as a result of essentially light falling on the surface. This light carries a force, and the force is of course a change in momentum, and so therefore if you bombard it with an intense radiation, you can actually cause something to move, because of course a pressure would therefore cause some kind of change in momentum, which is a movement. So there we go. I hope that was really informative, and I'll see you guys in the next episode. Take care.